Okay, welcome to part 7 of 2.2 bonding between atoms video. We are on covalent bonding still, and I think we can go through everything in this table. So, second box onwards, a covalent bond may be polar or non-polar. We'll talk about that, and you need to be able to what you need to be able to do is to use electronegativity values given, you don't have to memorize, or looking at the periodic table, so look at the position of the atoms to predict and explain the polarity of covalent bond. Indicate the polarity of a covalent bond using the appropriate convention. Next, covalent bonding is found in the molecule and non-molecular, which is continuous substances. Third last, a molecule can be represented by a molecular formula. There's a list that I will show you, and you must memorize them. A continuous covalent substance is represented by an empirical formula. So we'll talk about the terminology and how it's represented. And finally, the physical properties of continuous covalent substances can be explained using the model for covalent bonding. So physical properties. What you need to be able to do in that is explain the melting point, hardness, and electrical conductivity of continuous covalent substances. All right, so let's finish that up. Slide that I will be using is polarity part. So yeah, 46 onwards. All right, here we go. So firstly, covalent substances can be covalent bonds. Substances can be polar or non-polar, and at the same time, if you look into just bonds within molecules, they can be polar or non-polar. We will be giving you a bit of demo, so attracting water with a charged rod. You will see the polarity in action. Water is polar, by the way, and water has got polar bonds, so they're a bit different. We'll be looking at bonds here only. Polarity of the substances will be covered in topic 3 in detail, so let's focus on just each bond and polarity within it. What do polar and non-polar mean? So polar covalent bonds, they have got unequal share of electrons, like in this diagram here. So Cl is pulling electrons away from hydrogen. Why? Because chlorine has got higher electronegativity. That's all you have to say. Because chlorine wants to gain electrons and hydrogen doesn't really need it. It can donate its electron very easily, so they would have unequal share of electron. Whereas in non-polar bonds, electrons are shared equally. So something like between hydrogen atoms, like what's shown in that diagram there. So hydrogen atoms, two of them are sharing electrons with equal power. If you had Cl and Cl, you would expect the same as well. They would be sharing or pulling the electrons with same force. So that's considered non-polar. Things that polarity of bonds or polarity of molecules affect. We'll be looking at, again, demo. I'll give you chewing gum, not in the lab, and also give you chocolate. See what happens. We'll also watch the video for why don't oil mix and water mix. Now, let's talk about notation. When you talk about the polarity, you need to be able to use or understand different types of convention. What you need to be able to use is the delta notation. So you use the lowercase letter, Greek letter delta. It looks like a little apple. It's a bit of stem coming out. Is used to represent the polarized bond or polar bonds. It can be delta positive or delta negative. Delta negative being more electronegative atom within the bond. So in this case, in the case of HCl, there, HCl, what you can see is this. H having delta positive drawn on top and delta negative is drawn on top of Cl. That's all you have to be able to do. Okay, that's all. Other textbooks or other notations that you might find in the future is this, arrow and direction. So direction of arrow shows which side has got higher electronegativity and which way electrons are pulled towards. This cloud notation or diagram also shows which side has got higher electron density. So darker the green color is, in this case, has got more density of electrons. So that's what you can see. All right. So that's for polarity and nonpolar bonds. You can start doing it by looking at things like this. So when you look at the bonds within substances, so for nitrogen and nitrogen, there is no difference in polarity, electronegativity. So there is no polarity. It's not polar, it's not, so it has to be non-polar. So non-polar bond is here. Whereas for carbon and oxygen, if you look at this bond and this bond separately, let's focus on this bond. Oxygen and carbon, they have got different electronegativity. Now, if you look at the periodic table, oxygen is on the right-hand side of carbon. So oxygen would have delta negative, and carbon would be positive. So the bond between carbon and oxygen is definitely more delta negative. Or you can say that this bond is polar. As a substance, we'll talk about it later, but it's non-polar. Okay. So yeah, we'll look at the shape of molecule and the polarity of molecules later. I mentioned earlier that you have to know these molecules. These small molecules are very common, and it's going to be embarrassing if you don't know the formula if you're doing chemistry now. All right? So please spend some time to firstly copy down and try memorizing them. I'm pretty sure you know most of them, but NH3, it's ammonia. It's a common knowledge to me because it's something you can see in a cleaning agent like some bleach or toilet cleaner. All right, so that was for molecule. Molecules are small, lattice is big. What sort of big things can covalent bonds make? All right, some covalent substances do form large continuous lattices. It's called covalent lattice. For example, diamond or graphite. It's carbon only. Structure is a bit different, but lots of carbon atoms join together as maybe layers. So if you have thin layers and they're combined like so, they can come off very easily, and that's how you can write with a pencil. It's got graphite in it. Whereas for diamond, they're interlocked into positions and they're very solid because of that reason. Because they've got different structure, they have got different property, different feel, different look. But it's all made with carbon. Sand or silicon dioxide or silica, they are all made up of SiO2. Now, SiO2 has got, silicon and oxide, silicon dioxide. Now, it's joined in 1:2 ratio. Silicon to oxygen ratio is 1:2. And it's made in a regular shape, like so. And you can see diamond lattice happening, spinning around there, as well as silicon dioxide lattice. Both has got hexagon shape, and hexagon shape usually means fairly strong. And silicon dioxide makes up rocks. For lattices, you just look at the simplest ratio of what makes up. So simplest ratio, yeah, is shown with what's called empirical formula. SiO2, for example, is an empirical formula, so smallest ratio, instead of saying Si2 or 4 or Si3 or 6. It's just the simplest ratio. SiO2 is an empirical formula. Right, so properties of covalent bonds. If it's molecules, they tend to have low or lower melting points. That's because intermolecular forces are quite weak as well. If they don't have, a molecular substance contains discrete molecules with weaker intermolecular forces, they will be flying apart from each other really easily. The force of attraction between molecules is weaker than an ionic bond, so a boiling point or melting point of covalent substances is usually lower. Molecular solid have a much lower melting point than covalent network solid. So if you have got larger structures, they usually have got fairly high melting point compared to molecular solid. So if it's a small structure but becoming solid, they would have much lower. Some dissolves into water, so solubility is a bit different when it, depending on the structure. Some molecules do, and certain small molecules or contain polar sites. So if there are very polar sites in the molecule, they would dissolve into water. Water is actually polar as well. Carbon dioxide or sugar, they are big fairly compared to, sugar is quite big compared to carbon dioxide, but because sugar has got a lot of OH groups, which is highly polar, O and H, they can dissolve into water. But larger covalent lattices or contain no polar sites, such as diamond or silicon dioxide, graphite, they don't dissolve into water. Okay? You can also think of oil, fat, or protein polymer as big, large covalent lattices, which has no polar site. Okay, so here's a question, and that was the end of the chapter. Sorry, unit 2.2. Yes, unit 2.2. Yeah, we'll put more videos on one video on 2.3 after this, and that's it.